was going to come is already here. May I ask you to close the door?
Oh, yeah, sure.
Okay, first of all, there were homework problems, and some of you did not do the homework, so I will have to do it. So, let me start with exercise, quite an interesting exercise, and I believe I know how to do it, but if I do not, it might also happen that I do not. 4:14. F is a continuous mapping from the disk to the plane. Continuous. Proof. Either there exists a point Q in the such that FQ is Q, either this mapping leaves a point fixed, or there exists a point P on S1. S1 is the boundary of the disk, the circle. P1 on S1 and lambda greater than 1, such that f of P1 is lambda 1 P1, and there exists P2 on S1 and lambda 2. I think there is a misprint. I think one has greater or equal than 0. One has to take lambda 2 not simply less than 1 but positive, such that f of P2 is lambda 2 P2. Let me try to do this. I hope that I can prove it. So again, actually it is a strange kind of eigenvalue problem for a nonlinear mapping. It says that either we have an eigenpoint 1, or if this is not true, then we should have 2 points on the boundary, one with eigenvalue greater than 1 and one with eigenvalue less than 1.
Does D mean the open disk?
D means the closed disk. D means the closed disk.
S1 is the circle?
Huh? S1 is a circle, is the boundary of this closed disk. My feeling is that what we have to do, we have to introduce another mapping phi. Phi of P is simply, f of P is simply the old mapping for P in the disk. Nothing happens. And this is f of P over the length of f of P if P is not in the disk. If f of P, I'm sorry, bad. If f of P is in the disk, P is always in the disk. And if f of P is not in the disk, then this is. Let me try to explain what does it mean. This is the disk, this is a point P. Point P can stay inside the disk, and then I do not change anything. But if a point P goes outside of the disk, then I forcibly contract it so that it gets on the boundary. I forcibly contract it. Easy to see that this is a continuous mapping. This is obviously continuous mapping. Look at it and you will see everything is continuous. But now this new mapping is a mapping of the disk into disk. Because I bring all points that go astray, I bring them down. Okay? And by the fixed point theorem, there exists Q in the disk such that f tilde of Q is Q. A continuous mapping of the disk into itself must have a fixed point. Let us see what could happen. If Q is inside the disk, simply in the disk. Just a moment. Is inside the disk. If Q is inside the disk, this means the interior of disk. Then f of Q is Q is inside the disk. F of Q is inside the disk, and that means this is simply f of Q. If the f of Q is inside the disk, then f tilde of Q and f of Q do not. And in this case, we have exactly what is here. Let us consider the other option. Q is on the boundary. Q is in the closed disk, so it is either inside or on the boundary. Then we have f of Q is Q on the boundary. And what do we have here? There may be two options. One option is but this is also f of Q, right? No. Okay. So the question is, what is f of Q without tilde? F of Q must be, cannot be on in the interior. Cannot be in the interior, because if it was in the interior, if f of Q is in the interior, then f tilde of Q is f of Q, and f tilde of Q is here, a contradiction. So f of Q is not in the interior. So f of Q is either on the boundary or f of Q is not in D at all. That is an important point. Did I make this point? F of Q without tilde. F of Q cannot be in the interior. Because if f of Q was in the interior, then in this case f of tilde of Q is the same as f of Q. Look at the formula. And but f of Q is Q. It is on the S1. So I get f of Q is on S1, and this contradicts, these two guys contradict each other. So if f of Q is not in the interior, then f of Q is on the boundary or here. If f of Q is on the boundary, then f tilde of Q is the same as f of Q, and this is again the first situation. It is then this is true. Yes? And f, if, so from this the first option follows. The first option follows. If f of q is not in the boundary, then f tilde of q is f of q over length. I need another piece of chalk, and I do not have it. Here are several pieces of chalk. Over f of q. It is f of q over lambda. Lambda is greater than 1. Okay? And this is f of q is q. So considering these two, I've got at least the first one. Now, how do I get the second one? I think I also can get the second one. So I've got this. So either this or at least this, and I have the other. I need to do it, and I think there is a way to do it. Oh, definitely. This is easy, and let me explain how. Okay. I may assume that f of, say, r is not 0 for all r in D. Because if it is 0, then the second part is done with lambda equals 0. And then I can do the following.
P2 has to be on the boundary.
I meant exactly this. Okay, I think that there is a little additional work to do, and I can prove the second, but I have forgotten how to do it right now. I'm sorry. So let us leave it as a homework for everyone. I think that it is not a big deal. I think this is not a big deal how to do this.
It looks odd.
Huh?
It looks odd.
Why?
Well, if I take the disk and I just shove it on the other side of the board, I've taken every point, mapped it outside the disk. And how can I satisfy it?
And then for the left edge, you have the farther edge and the closer edge.
Yes, you're right. This is a strange situation because consider simply, I will find this nevertheless.
You shift it in one direction, this boundary goes back here, this one goes back to the other side.
No. The thing is very simple. Consider the following mapping. Take a disk. Okay, the thing is that actually that is. But nevertheless, it is not true either. Take a disk and shift it far away. If you, no, there is a point with, if I do not require lambda 2 to be positive, then one of them goes to minus itself. I think that this already, give me a minute and I will try to. Okay, I will try to do it next time. It's not that. I have proven that either this or the first, and I need to prove additionally that either this or the second. Okay. Sorry. Yesterday at 11 p.m. I was sure that I had a full proof. Maybe at 1 p.m. a.m. I don't remember at which time did I think that the proof was here.
We can solve lots of problems. at
Mhm.
the time.
Yes, at that time it is a very special time for solving problems.
Right.
Then there is another beautiful problem, and I hope that I got it right. F is a continuous mapping of the circle into itself, continuous. And it has no fixed points. Prove the degree of F is 1. Degree of F is the winding number of the, well, S1 is a circle, its image is a closed curve, and I must consider the winding number of this image. Okay? Very good. And I think I know how to do it. Take any point P. Let this be f of P. P is never f of P. This is the condition of no fixed points. So consider the vector going from f of P to P. It is a vector, so it has a direction. Take the midpoint and draw the perpendicular to the right. The notion of right is well defined because we have a vector. The notion to the right of it. It will eventually meet the point to the right. That is important. And let this denote f tilde of P. So f tilde of P is a continuous mapping S1 to S1. A continuous mapping. Also, no fixed points. Obviously. This cannot be this, because this segment is non-trivial, always. Now I think I know what to do. Consider the degree of f. I first prove that it is 1. And then I prove that degree of f is the same as degree of f tilde. This will give me exactly what I need, correct? Why do I know that the degree of f tilde is 1? Because of the dog on the leash. Connect these 2 points. This is the leash between them. And the leash is never going to hit the origin. Why? Because this angle, this is never greater than what? Is strictly less than 360. This arc is strictly less than 360, because if it is equal to 360, you will have f of P equal P. So this arc is strictly less than 360. Therefore, this arc, it is half of that arc, is strictly less than 180. Yes? And if the arc is less than 180, this segment has no chances of hitting the origin. So the leash never touches the hydrant, which is a very important fact in mathematics. Okay? So by the dog on the leash theorem, the degree of the identity mapping, P goes to P, and the degree of the mapping f of P are the same. But the degree of the identity mapping is 1, and therefore the degree of f tilde is also 1.
How did you show that f tilde has degree 1?
Again, let fp go around here. What is the winding number of this curve? 1. This leash never touches this point, the winding number with respect to the origin. This never touches this. Therefore, the winding number of this curve, f of p, must be equal to the winding number of p. If the owner does not, the owner and the dog make the same number of rotations around the what? Around the hydrant. Okay. So I have proven this, have I? Was I convincing enough? Then actually now I need to prove this. But I consider this leash. This leash is also never touching the hydrant, the origin. And therefore the degrees must be the same. This was true yesterday at 1, today at 1 a.m. and a good sign that it is still true. Is it nice?
Everything is true for 12 hours.
Yes. Actually, there is a, well, meta theorem. Everything that is true for 2 days is true forever. Okay. Let me skip, not very difficult, 16 and 17 and do 18. I like.
F must be surjective.
Well, that it is because that if it is not surjective, then okay, it's easier. So F must be surjective.
You have to remind some of us what surjective is.
Surjective onto.
Ah.
If it is not surjective, that means there is a point which is not an image of anything. But actually there is a whole interval which is not in this case, because the circle is compact, the image of compact is compact and therefore closed. Okay? That means that there is a way from here to here. And as I move the point from here to here, the winding number around this point does not change. And if I move very fast, very far away, then the winding number should be 0. I'm not crossing, I'm not going around a very remote point. And therefore, should I explain it in more details?
No.
Mm-hmm.
As P goes around, it pushes F around with it.
Yes. Mm-hmm. Mm-hmm. Now there is an infinite dimensional problem. Just to explain that things are not as good in infinite dimensions as they are in finite dimensions. I want the last problem. Let me consider, it is 418. Let me consider the infinite dimensional ball. It is a set of sequences such that less or equal than 1. Infinite dimensional ball. It is a ball in the Hilbert space of sequences. Find a continuous f d infinity to d infinity without fixed points. So it is well known that the unit ball of the infinite dimensional Hilbert space is not compact in the norm topology, and we should not expect this set to have a fixed point property. And in this case, I think I know how to construct a mapping without fixed points. And actually, every person in functional analysis also knows this. How can I do this? Okay. I will make a shift operator. Shift takes a sequence A0, A1, and so on, and produces the should I take the right shift or the left shift? It doesn't matter.
You better take a right shift.
Just a moment. No. Actually, it doesn't matter.
What would you do with A0?
Yes. Obviously, this is a mapping from the sum of squares, does not depend. Yes, I should take the right shift. Well, I could have taken the left shift as well, but okay, I don't. Then no, they will be. They could be a fixed point. Right shift only. Right shift. Okay. Definitely, the sum of squares does not depend whether I add 0 in front or not. Okay. So S is a mapping from d infinity to d infinity. And this mapping is obviously continuous. Check. Not a problem. This mapping preserves the norm. Come on. It is linear, preserving the norm. And there is no fixed point, because assume there is. That means A0, A1 is. It is a linear. Okay, I will deal with that. Yes, you're right. There's every linear mapping has a fixed point which is 0. So I have to deal with this. Just a moment.
So insert non-zero in the first position.
But then it is going to be not the sum of. It is not. It will not.
So put there something so that the sum of the squares becomes equal now. It will not be linear then.
But the thing is that if the sum of the squares is exactly 1.
Then you'll get
Oh, then yes. Okay. Thank you. Say lambda. Lambda is 1 minus square root of 1 minus A0 squared minus A1 squared minus and so on. This is a nonlinear mapping. Yes, it is because when I was geometrically doing this, I was doing exactly what you said. I was moving one dimension each. Yes, but I decided that this is, yes. Okay. First of all, it is definitely a mapping from d infinity to d infinity. Actually, it is even a mapping from d infinity to the sphere. And it is not what? It has no fixed points, because if it had fixed points, then we would have this. And that means that A0 must be equal to A1. A1 must be equal to A2. Okay? And it follows that all of them must be zeros. Because if they are not zeros, then the sum of squares does not sum up to 1. It is not finite, simply. Okay? So if it was fine, then it is 0. But in this case, I would have got 0, 0 equal to, this is 1, which is not so true. So in the infinite dimensional ball, there are continuous mappings which have no fixed points. This is the truth, but not the whole truth. Because in infinite dimensional space we have numerous topologies. One of the topologies is the so-called weak topology. In the weak topology, the unit ball is weakly compact. And by Leray-Schauder, it does have a weakly continuous mapping of the ball into itself, does have a fixed point. The thing is that this mapping is not weakly continuous. It is continuous in the norm topology, but not weak topology.
What do you mean by weak?
I can explain it. Let me explain it in a simpler way. If I have AI in the ball, it is not, these are sequences. Each of them is a sequence. I say that AI converge to A if for any B in the Hilbert space, AIB, scalar product, converges to AB. It is known that in the weak topology, the unit ball of the Hilbert space is compact, because the Hilbert space is a dual space, self-dual space. And by Leray-Schauder theory, in this case, a weakly continuous mapping of the ball into itself must have a fixed point. But this mapping that I have suggested here is not weakly compact. Is not weakly continuous, sorry. So there's a lot of interesting things popping up in infinite dimensions, and this is one of them. So do not expect infinite dimension to be as simple as the finite dimension, though to a very large extent it is simpler than the finite dimension.
So you're saying here that there's like a topology on functions. So you're saying that
It is the topology on this unit disk, and the elements of the unit disk are infinite sequences. If you wish, infinite sequences can be viewed as a function on the natural numbers. For each natural number we have a value. Okay. So this is, okay, I just wanted to, okay, let us move on. Last time I made a very fast review of ideas leading to a very important practical knowledge how to fairly cut a sandwich. But since I was doing very fast, the sandwich was cut not exactly fairly, and I have to revisit the whole procedure. Let me quickly remind what we did last time, though we did it, so I can simply remind it. Lemma is due to Borsuk, a Polish topologist. let f c to c prime be a continuous mapping. And c and c prime are two circles. C and C prime are two circles. Not disks, but circles. And assume that f of p star is f of p star. On a circle, we have a notion of an antipode. And if I take an antipode here and map it, it goes to an antipode. What is the right way to pronounce it? Antipode? Antipode.
Either.
Anti is okay, okay?
Yeah.
Oh, that's much better. It is much closer to the Russian pronunciation. Okay. So then the degree of f is odd. A strange result, odd result, but quite understandable. Let me just remind you, though it will not be an accurate proof, but remind you how I do this, how one can do this. This is C, this is C prime. Take this part, half of C. It maps, this point maps here, okay? And where does this point map? To the antipode, correct? So the image of this will be a curve, maybe going this way, but starting here and ending here. Maybe it will go several times, but it is going to end here. Correct? But what is the change of the argument of the angle of this curve? The change of the angle is 2k pi plus pi over 2. When I go from here to here, the change of angle is pi over 2, correct? And actually I can add to it 2k pi. Or if I divide by 2 pi, I would get k plus 1/2. But now let me consider the second half, this curve. What happens to this curve? Plus pi, definitely. I put this over 2 a bit. I knew that there will be 1/2 in the end. That's why I put it in advance. What about this part? Actually, it is going to be the same curve. Why? Because this point is the antipode of this. This point is antipode of this, correct? And antipodes must go to antipodes. So actually, I will get another curve which is symmetric to this curve by rotation by pi, correct? So its change of the angle over 2 pi will be exactly the same, because this is essentially the same curve, only rotated. So what is degree of f? It is this change plus the change of the other part, additivity of change. K plus 1/2 plus k plus 1/2 which is 2k plus 1, which is definitely odd. It is a deep result, though it seems to be very easy, but it is a deep result. So if there is a mapping, we need to have a better understanding what is antipodes. Antipodes are involutions with no fixed points. That means if you apply antipode twice, it will return where you were. It is called an involution. Okay? And it has no fixed points. So actually, if you have a mapping, if you have two spaces with each of them has an involution without fixed points, and you have a mapping preserving this involution, that is exactly why star is a usual notation for involution. Then you have something like Borsuk lemma. But I don't want to go into it. Geometrically, it is clear what it is. This is point number 1. From this simple result, I can derive a number of important corollaries. Lemma, a very important lemma. There does not exist a continuous mapping F of a sphere to a circle such that f of p star is f of p star. We have a notion of antipode on the sphere, and we have a notion of antipode on the circle. And there does not exist a continuous mapping, of the sphere, it is two-dimensional object, to the circle, one-dimensional object, which preserves antipodes. And the way to prove it is this. The way to prove it is this. Consider a disk. And let us build a sphere with this disk as the central section. And let us construct a mapping from phi, from the disk to the circle. A mapping from the disk to the circle. How do I construct it? Continuous mapping from the disk to the circle. And I construct it in a very special way. Namely, take a point on the disk. Raise it perpendicularly until it reaches the sphere. And then apply F to this point on the sphere. So definitely assume the opposite. F exists. And construct a mapping of the disk to the circle. So first from the disk I go to the upper hemisphere. Because the life is usually better above the equator. Okay, and then I go here. As a matter of fact, I can, without any loss of generality, I can assume that. Okay, I don't even need to assume that. I just wanted to make some better things, but no, I do not need to assume that. So that's what, because it is a composition of two continuous mappings. Phi is continuous because it is a composition of two continuous mappings. Now, consider phi restricted to the boundary of the disk. Boundary of the disk is a circle. If I am on the boundary, I do not go up. I stay where I am. Okay? It is simply f restricted to this. Yes? And let me call it let me call it phi capital, this mapping. Phi capital, I call this mapping phi capital. Phi capital has the following property. Phi of p star is phi of p star. Why? Because if I am on this boundary of disk, then if I'm here, then the antipode is also here. Correct? Antipode is also here. And this property is true for f. So it is true for phi capital. This property is true for f, and therefore it is true for phi capital. So I was able to construct a mapping phi from dd to c, correct? Which has this property. What does Borsuk tell us in this case? I'm in the situation of Borsuk lemma. So degree of phi is odd. Degree of phi is odd. But actually degree of phi is 0. Why? Because the mapping phi can be extended to the whole disk. Phi is a restriction of a mapping of the whole disk to the circle. And therefore, if I, instead of this circle, will take smaller and smaller circles, the degree is not changing. It is changing continuously, but it is an integer number, and integer number changing continuously is constant. Correct? And when I get to the 0, it is a constant curve. Correct? And it has degree 0. And 0 is never odd. Very good.
Something I don't understand about the proof, you really only used
The upper
half plane.
Yes.
Or the upper half sphere.
But actually I do not need anything else. I need to know, yes, actually this theorem can be yes, this theorem can be done for a disk. There is no mapping of the disk into there is not of a sphere, but I will need sphere for application. And there is no continuous mapping of the disk into a circle with this property. But actually the notion of an antipode in a disk is a bit not very good. So this is a reasonable. Okay. Have we done this?
Yeah.
Yeah. Now I will prove one result more. Again, I did it last time, but it is better to. The result becomes even more true when it is proved twice. There was an interesting story in Memoirs by Kolmogorov. When he was a student, he was choosing between mathematics and history. And he even wrote a paper about, say, Russian antiquities. And he brought it to his supervisor. He said that, okay, and where he claimed that he has proven that something happened in Novgorod. Novgorod was one of the centers of Russian culture in the 10th century. He proved that something happens there, but the advisor said that this is not enough. You must have not one, but several proofs. And he decided he better choose something where one proof is enough. He was very upset about that.
Well, that's right. I do remember a long, long time ago when Russians in the United States were very rare in the 1960s. There was a visitor who came from Russia and gave a talk, and he had something to do with cosmic rays, and he said 7 reasons for believing something. He listed them on the blackboard, and then he said he would be much more convinced if he only had 1 reason.
Yes. Okay, now the Borsuk-Ulam theorem. By the way, both of them are Polish.
But Ulam spent most of his life in
Yes.
adulthood, at least.
But yes, yes, but both of them are Polish. They come from the Polish mathematical school. Okay.
Ulam is a good source of stories.
Yeah. Let F be a continuous mapping of a sphere to a plane. Sphere to a plane, that's important. There exists a point in the sphere such that there exists 2 points such that f of p equals f of p star. A very unusual theorem. Actually, nothing is required. Any mapping from a sphere to a plane. Then there exists a point, there exists a pair of antipodal points at which this function takes the same values. This is not a function, this is a mapping. So it is a couple of functions. It is mapping to R2, so this is a couple of mappings. A wonderful result. And the proof is actually wonderful. Assume the opposite. And let us consider such a new mapping. In this case, I can always assume that P star is minus P. I can consider that the sphere is the standard sphere centered at the origin, correct? And P star is minus P. If I assume the opposite, that means f of p is never f of minus p for any p in the sphere, and therefore this function is well defined and continuous. So assuming the opposite, I assume that the denominator is never 0. So G is a mapping of S2 to, where does it map? It maps to a circle, because G of P is always on a circle, isn't it? Yes? Continuous. And G of P star, it is G of minus P. Look what happens if I replace P by minus P. Nothing happens in the denominator because of the absolute value, correct? And in the numerator it will be minus G of P. Yes? Which is G of P star. But this lemma says that there does not exist such a mapping from the sphere to a circle with this condition. It does not exist simply. So my assumption has to be wrong, should better be wrong. So, isn't it nice? It looks very much like a trick, like a carefully planned scam, which it is. We're done. Do you like it? Just watch. Up to now we have used.
Always so easy to have a theorem.
Well, it is if you follow a long sequence of good, well-selected propositions, then each step is easy. So the result is, if you have a three-piece sandwich, you can always cut it with one plane so that each piece will be cut exactly in halves by volume. The plane is unique. No, there is a plane, not unique. There is a plane such that this is happening. So a good cook should be able to do this with one cut of a knife. I will need this. Okay. Oh, actually I will need this, but we remember this. Let me do some preparation first. Imagine that we have we live in space, in three-dimensional space, and we have one bounded body, one bounded solid. This solid is closed and measurable, so the notion of its volume is well defined. Let me enclose it into a sphere, huge sphere. It is bounded, it's possible to include it into a huge sphere. Take a point on the sphere, P. This is the antipode, P star, and join these 2 points. We will have a line, a diameter. Okay? Now let me take the plane perpendicular to this diameter and move it along this line. When it is here, actually I can say that this is cut into pieces. One piece is everything, the other piece is empty. Can I do it? I start moving. At some moment I will really cut it into 2 pieces. One is this, the other is this. And when I move it here, then again 2 pieces, but now this piece is empty and this piece is everything. Correct? A statement which is not proven but can be understood. It requires actually the understanding of what the volume is. The part of the volume on one side of the plane is a continuous function of the point at which the plane intersects the diameter. As I continuously move the plane, the volume of the part on one side is a continuous function of the point.
Do I believe that?
I think we all believe for a simple reason. If I move a little bit, the volume is going to change.
Here's my line.
Mm-hmm.
I'm going to take the plane is perpendicular to this line. And here's my volume, which is a rectangular solid.
Mm-hmm.
At some point, I reach the rectangular solid, and all of a sudden,
Nothing happens?
Under the objects. All you said is that.
because it's volume.
It's volume.
It's not,
Mhm.
it's not anything.
Mhm. Nothing happens.
The derivative is not.
Well, we are not talking about derivative. Derivative may not exist, but continuity. Because if I move the plane a little bit, what is the change of the volume? The change of the volume is the volume in the layer between 2 planes. But the layer between 2 planes is the volume of the layer between two planes is smaller than the layer of the ball between two planes, correct? And the layer of the volume of the layer of the of the ball between two planes is what? Approximately the height, which is small, times the area of the section. So believe me, this I think that everyone believes. Okay. But that means that there will be a point at which this particular body is split into two equal halves. Because at first the volume on this side is 0, is everything. At this moment it is 0, it is a continuous function, then it must take all intermediate values. So this is the point, I call it a point Q of P, and I will call this A. A is the name of the body. So Q of PA is the point on the segment P star, such that volume of A half space, you understand what I mean, is 1/2 volume A. There exists such a point. So let ABC be 3 bounded closed measurable bodies inside a sphere. Then we have 3 functions, Q of PA, Q of PB, and Q of PC. These are functions from the sphere to the related segments. Okay, now construct a new function. Q of PA minus Q of PC, Q of BA minus Q of BC. It is a mapping from a sphere to R2.
I don't have to understand the second half. Q of PA, did you mean?
Oh, PA.
Yeah, yes,
PA and PC. Obviously continuous. But there is one thing more that I forget to mention. Q of P star A is the diameter minus Q of PA. Is it clear or not? The segment is exactly the same, but I switch which path I take. So this mapping, I call it phi of P. Phi is a mapping from the sphere to the plane. And what is important, phi of P star is equal to phi of minus phi of P. Just compute it. If I put P star here, what will happen? It will be D minus the same, minus D minus the same. D and D cancel out. I get them reversed, correct? And the same here. Because of this formula, I have this condition. Again, if I put P star here, what will happen? D minus it, D minus it, D's cancel out, and I get what I need.
You realize, though, that belatedly, the two parts of phi are the same. One of those should be P and
PB, PB, yes. PC, PB, PC, yes, you're right. Okay, now let me invoke the antipode theorem, which says, for each mapping from here to here, there exist two antipodal points at which this mapping takes the same values. So there exists P naught on the sphere such that phi of P naught is phi of P naught star. But this is true for any point P. And this is true for one point. So for one point, both these guys are true. Yes? When this can be the same, when these two can go together. That means there exists P naught such that phi of P naught is 0. 0 is a vector. What does it mean? This equals to this, and this equals to this. So there exists a point. So that if I take the segment from this point to the opposite point, then points on this segment at which the perpendicular plane cuts all of them in halves are the same. So did we prove that? Not bad at all, isn't it? I want to repeat it once again, and it seems as if I'm within the allotted time yet. So let me do it this way. Consider such mapping. It is a mapping from continuous mapping, continuous because everything is continuous here, from the sphere to the plane. A very important property of this mapping is that it takes antipodal points into minus each other. Where does it come from? It comes from this simple observation. D is the diameter of the sphere. So if I put stars here, then a simple computation shows that everything is okay. But on the other hand, the antipodes theorem tells us that there always exists a point on the sphere such that the value of continuous mapping to the plane at this point and at the antipodal points are the same. This equals this. But at this point also this equals this. That means that this must be true. This is true, that means that this is 0 and this is 0. What does it mean? There is a point such that the same plane passing through the same point cuts all three bodies into pieces at the same time, into equal pieces at the same time. And a good cook or a good bartender should look for this point exactly.
Am I correct in saying, without using any topology, that think of the bodies as being uniform density,
Uh-huh.
and then find the plane through the center of mass of all three.
That is interesting. It seems to be exactly right. It is a proof. Just a moment. Give me 1 second. You're absolutely right. This is exactly it. Because the center of masses has the property that if I draw any plane through the center of masses, then the two halves have the same volume. It is the definition of the center of masses. And if I have 3 bodies, then they have 3 centers of masses. There is exactly 1 plane going through them. By the way, this also proves that this plane is essentially unique, up to some generations where 2 centers of masses coincide. But this cannot happen with any, say, in a real sandwich. Okay? Then you are absolutely right. This is a wonderful proof. This is a wonderful proof. Yes, absolutely right. So, take 3 bodies, takes 3 centers of masses. You have to prove, though it is quite easy, that the center of masses do exist. Yes, yes, they do exist. But assuming, since there is no physicist with tenure who doubts this, then on the physical level of rigor, it is an absolutely good proof.
Can we call this the stone Tukey Delos theorem?
Yes, sure. Delos Tukey stone.
So if your bread is non-uniform density, then you just define some sort of
Yes.
volume.
Yes. Center.
Exactly equivalent.
Mm-hmm.
I don't even need continuous, isolated mass. I just label them different.
Yes. Brilliant. Absolutely fantastic. But actually, if you cut a sandwich, you do not so much worry about the volumes of what you get, but rather about the masses of what you get. And if you are worrying about masses, then this is exactly the way to cut. Because who worries about the volume? Okay. So next time I will finish this chapter with all remaining. First of all, I expect that everyone will be doing their homework, and I will finish this chapter about topology, and it is open to anyone else to take over. And I mean exactly someone else.
Epistemology next?
The next Wednesday, I think it is de Rham complex and homologies. Could you do this?
Sure.
Uh-huh. Okay, so I will announce you next time. No, I'm sorry, next time I'm still finishing this, and the time after the next, you're very welcome. Great.